In this video, we'll break down how does RAG, Retrieval-Augmented Generation, actually work behind the scenes and the complete RAG pipeline. Let's see what actually happens under the hood. Let's look at the basic flow of a chatbot. A user asks a question. The question goes to a large language model which processes it and generates a response. But there's a problem. The AI model may not have access to your project-specific or domain-specific data, so the response may not always be accurate or relevant. Now imagine your organization's knowledge is spread across thousands of PDFs, Word documents, wikis, and databases. How do you give an AI model access to all that information? That's where RAG, Retrieval-Augmented Generation, comes in. So why is it called RAG? First, your query and prompt are used to retrieve relevant information from your knowledge sources. This is retrieval. That retrieved information is then added to the original query as additional context for the AI model. This is augmentation. Finally, the AI model uses the query and the retrieved context to generate the response. That's generation. Now let's visualize the RAG pipeline step by step. First, we collect our documents. Next comes chunking. Large documents are split into smaller pieces called chunks. Why do we split? Because we don't want to retrieve an entire document when only a small section is relevant. It can be achieved through different strategies such as fixed size or semantic chunking. An embedding model converts text into a numerical representation called an embedding vector. You can think of this vector as representing the text in a mathematical space. Texts with similar meanings can be represented closer together in that space, depending on the embedding model and the similarity method being used. Let's visualize this with a simple example. Imagine we have words like byte, programming, database, car, and weather represented as points in a three-dimensional embedding space. Each point represents the embedding of a piece of text. Now our query is byte. The system converts that query into an embedding and looks for nearby vectors. Notice how the points representing semantically related content are closer to our query, while unrelated content is farther away. The retrieval system can then rank these candidates by similarity and select the most relevant ones. Once the embeddings are generated, they can be stored and indexed in a vector database or another system that supports vector search. Each embedding is associated with its original chunk or a reference to it, along with relevant metadata. Just like our documents, the user's query is converted into an embedding using the same embedding model. Now we have a vector representing the user's question. The system compares this query vector with the vectors in our vector index and performs a similarity search. The most relevant matches are identified and their corresponding chunks are retrieved. The original question is combined with the retrieved context. This gives the model additional information to work with when generating its response. Finally, the augmented input is sent to the large language model. The model uses the question and the retrieved context to generate the response. But why can't we just store these chunks in a normal database and search them? Because RAG isn't only looking for matching words. It needs to find semantically similar information. A vector search system can index these vectors and use nearest neighbor search to efficiently find the most relevant ones. Metadata, indexing, sharding, and batch or streaming ingestion help manage this knowledge at scale. The result is efficient similarity search, finding relevant chunks without having to scan the entire knowledge base in the same way. And that's the key reason vector search is so useful in RAG. Now, when should we use RAG instead of fine-tuning the model? So if the problem is how the model should behave, fine-tuning may be appropriate. If the problem is what information the model needs access to, RAG is often a better fit. Fine-tuning changes the model. RAG changes the context. So why is RAG so widely used? There are several reasons. Latest information. First, retrieval can provide information from an external knowledge source instead of relying exclusively on information encoded during model training. Reduced hallucinations. Second, grounding an answer in retrieved evidence can help reduce unsupported responses. It doesn't guarantee that a model will never hallucinate, but providing relevant context gives the model additional evidence to work from. Enterprise knowledge. Third, RAG makes it possible to connect an AI application with domain-specific knowledge. Private data. RAG can also retrieve information from internal or private sources, subject to the application's security and access controls. Better retrieval precision. And finally, depending on the use case, retrieving relevant information can be an alternative to modifying the model itself through fine-tuning. Real-world examples where RAG is widely used are customer support, enterprise search, healthcare and legal applications, and developers. The common pattern across all of these use cases is simple. The model doesn't need to know everything itself. RAG gives it access to the right information when it's needed.